Well, the first, I guess, real example of a rate of change that you may have seen before is growth and decay. Now, this first model that we're going to look at is a very, very basic model. It's basically the 2-unit idea we start with, and then we extend on that. So extension then takes it a little bit further. So the first basic idea is this: growth and decay is proportional to the population. That makes sense. More people you got, the more people that are going to die, more people that are going to be born. That's the theory anyway. So we could write that as a rate. The rate of change then, if it's directly proportional to population, then it must be equal to some constant times the population. Well, this is in terms of P. So to try and get an equation out of this, I'm going to turn both sides upside down. So now the left-hand side, the derivative, is also with respect to P. So they're both with respect to P. So the T to P is 1 on Kp. So therefore T is 1 on K times the integral of dP over P. Well, the integral of dP over P is log P. We've got the derivative on function. So we get 1 on K log P plus, of course, a constant. Okay, so playing around with this, because we want a formula for population. So we want to make P the subject. So I've got Kt is log P plus a constant. Log P, Kt minus a constant. To undo the log, exponentialize, again if there is such a word. So P will equal e to the power of Kt minus c. I'm going to rewrite that by using index laws and write e to the Kt times e to the minus c. So c is just a constant. So therefore e to the minus c is also just a constant. So instead of writing it as e to the minus c, we can say, oh well, P is equal to some constant times e to the Kt. Now that's the beautiful way that the formula is derived. The unfortunate thing is they suck the life out of this topic, in that you can just jump and say, oh, if the P to T equals Kp, oh, the solution is P equals AE to the Kt. You just bang, quote the solution straight away. Very boring, I know, but and unsatisfactory, and I know you're all upset about that. As I was when they decided to do it that way. But that's where it comes from. I mean, simple rate of change question. So let's define a few things. So P, well, if we're talking about population, then population at time t. Capital A would turn out to be the initial population if you think about it. Because when t equals 0, e to the Kt will be e to the 0, which is 1. So A is the initial population. K will be whatever the growth, or if it was negative, it'll be a decay constant. And T, of course, represents time. So we're going to look at some little bacteria. The growth rate per hour of this bacteria is 10% of the population. So the initial population is, how many zeros have I got there? 1, 2, 3, 1 million. We're going to show that this is a solution. So this is the way they tend to set the questions up. They're going to say, show that this is a solution. So rather than going through and starting with the P to T and integrating it like I did, we're starting with the answer and showing it satisfies the initial equation. So our one they've given us is P equals some constant E, and the growth rate is of course 0.1, 10% of T. So if I differentiate that, I get the P to T is 0.1 AE to the 0.1 T, but hey, P is AE to the 0.1 T. So the P to T equals 0.1 P. So it satisfies the problem. The growth rate is 10% or 0.1 of the population. All right, we're now going to find out how many bacteria is now crawling over you after 3.5 hours. Initial population, so P will end up being 1,000,000 E to the 0.1 T. That really is just substitution question. T equals 3.5, sub it in, and we've got 1,419,000. So there we go, after 3.5 hours, 1,419,000 bacteria. On an island, the population in 1960 was 1,732. But the people on this island don't like each other very much, apparently. Because in 1970, it's 1,260. So they're dying, they're decaying. Find the annual growth rate, although it's actually going to be a decay rate, assuming that it is proportional to population. Okay, so they've told us the P to T is equal to some constant times the population. Oh, what do you know? The solution to that is AE to the KT. Okay. Now, they told me the initial population was 1,732. So A turns out to be 1,732. So here's my formula, 1732 e to the KT. We need to find that growth rate. The other piece of information they've given me, in 1970, it's 1,260. Be careful, don't sub in T equals 1970. T is of course 10 years later. Okay, so e to the 10k, there's the exact value. K equals 1/10 log 1,260 over 1732. You might want to store that number in your calculator, something like that, so you're using the exact value rather than an approximation. Although to answer this one, it did say to the nearest percent, so let's work out what that is. Negative is 0.03, so negative 3%. So in how many years will the population be halved from that initial population? So we now want to know when the population is 866. So when is e to the KT a half? KT equals log a half T equals... It's a shame you don't do that half-life stuff with radioactivity anymore then, because that's where the formula comes from, basically. That's essentially what we're working out. It's not a radioactive element, it's a population, but we're still finding the half-life. So T is 1 on K, log a half. K, of course, is that number we just worked out before. And when we sub that in, we get 21.786. So the interesting question here is, in how many years will the population be half that? How do we answer this question? Do we assume they're looking for complete years?
22.
Well, 22 satisfies both the rounding rule and the logical rule. What about if that was 21.4?
Obviously half yet. Would you still say 22?
Yeah, I think I'd still say 22. Because at 21 years, it hasn't been halved yet. So, but I think what I'd definitely do is I'd write that down first, so that, they can see why I've gone the way I have. They can say, well, yeah, I did get the correct answer on the calculator. You might even justify, if it was 21.4, you might even justify yourself by saying, well, after 21 years, it hasn't halved yet, or something like that, to be 100% clear. So 22 years, it's been halved. Okay. 7J.